Now we're going to generate irreducible representations from our reducible representations that we have for the linear combination of atomic orbital wave functions that we have generated for the oxygen atoms. Okay, this will help us determine what the nature of our salks are. Okay, so remember this one, the C1, right, was generated from 2s atomic orbitals for this, and so we had this reducible representation. And so we go back to our character table here, and so what we can find is that we are looking for the specific addition of two of these representations, these irreducible representations that allow us to generate this, this reducible representation here. And so what this comes from is we can see that this is the addition of the AG representation, which is 1, 1, 1, 1, 1, 1, 1, 1, combined with the B1U representation, which based on our table is 1, 1, minus 1, minus 1, minus 1, minus 1. Let me read that. 1, 1, right? And so if we just add down, right, we see 1 plus 1 is 2, 1 plus 1 is 2, negative 1 plus 1 is 0, 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 1 plus 1 is 2, 1 plus 1 is 2. And so what we can say then is that the combination of the AG plus the B1U yields the reducible representation represented for the first wave function here, generated from the 2s atomic orbitals. And so what we can say here is gamma, we refer to this as A1G plus B1U, all right? The second wave function, right, C2, which was generated from the 2pz atomic orbitals, right, has the same reducible representation, and so we expect it to also have to be the same combination of the reducible representations, or irreducible representations, okay? We can do a similar process for each of the other combination of atomic orbitals, and what we find is that the one generated from the py orbitals is B3G plus B2U, and then the last one is generated from the combination of B2G plus B3U, okay? Now, this set is fairly easy to just combine from the character table by inspection and figure out what these reducible representations are. But sometimes that's not always possible. So there's another way to doing this where, for instance, right, if we look at our character table, right, an important thing is like, for instance, the AG, right, we have the irreducible representation, which shows 1 across each of the symmetry operators, right? And what we can do is we can determine the coefficient for gamma for an A1G, for instance, by doing the following process. So what we do is we multiply our the number from our irreducible representation for instance, C1, right, is 2. And we multiply it by the coefficient in front of the symmetry operator, which for all of these is 1 right now. Like in other character tables, these will have different numbers in front of them. And then we multiply it by the corresponding place in the AG of E, which, just as a reminder, is 1s across, so 1. Okay, and we do that for all these symmetry elements. Okay, so 2 plus, this would be equal to 2 times 1 times 1. This is going to be equal to 0 times 1 times 1. Same here, which of course is 0. Right, again, plus 0, plus 0 plus 0 plus 2 times 1 times 1 plus 2 times 1 times 1, right? And what we end up with is 2 plus 2 plus 2 plus 2 equals 8. We're going to divide that by the total coefficients in front of these symmetry operators, so it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. That's going to be equal to 1, which means that a reducible representation can be broken down into one A1G irreducible representation.